Okay, up until now, we have been working on the sprinkler side of the system, determining the water requirements in terms of gallons per minute and pressure. Now, we need to see if we have the water out in the street to meet those requirements. And what we're going to do is estimate water supplies. As with all my other videos, this is a disclaimer. This is for entertainment purposes only. These are water estimates. No final determination of adequacy or changes to a sprinkler system should be made without a full flow test or calculations acceptable to the authority having jurisdiction. Now, the easiest way to get a water supply is to contact the water department for the municipality, or in some cases, the fire department may have that information. And if they do have that information, it's great. So we don't need to make any estimates. And hopefully, as I indicated in the last video, you should have looked at any number of YouTube videos on how to conduct a water supply test. And it's basically putting gauges on one hydrant, flowing another hydrant. It's actually a pretty simple operation. And from that, you should have learned a few terms, which would be static pressure, which is the no flow pressure, and residual pressure, that's the pressure when there's flow. You're flowing through these hydrant butts, generally 2.5-inch butts, and there'll be an outlet coefficient, and hopefully they discuss that in the videos. And based on the internal configuration of the butt, will have a play in the overall GPM. And of course, from that information, where you put a pitot tube in the flow stream, you'll get a pressure, and based on the size and the pressure, you'll be able, through these discharge tables, to determine a flow in gallons per minute. They may also provide you with what is an effective point. So, for instance, the effective point will be in a variety of places depending on the flow of the water in the street. And I'm not going to discuss that in any detail, but know that they may provide you with that information as well. I want you to know there are some serious limitations on water supply testing, even when they're done with the full flow test. And that is, first, they're only as good as the person conducting the test. And having flowed a lot of hydrants in my day, I can tell you that there's a certain art to getting the right number. So much so that when we used to do the 8-hour class, we would have 15, 20 people in the class, and we would all go out and flow a hydrant and put the pitot tube in the stream, and we could have a 10 psi variation between students as to what the right number, or what the number was off the pressure gauge. With lower flows, it's not so difficult to cut into the stream. With really high pressures, it's difficult to get a good reading. So I always would look at who was conducting the test. Pressure gauge accuracy, the gauges need to be calibrated. I'll go into that in more detail. Pitot condition, the actual device that's stuck in the stream, has a play in the overall number, the pressure that's converted to a GPM. Time of day, so conducting the test at 3 in the morning will provide different information than if you conduct it at 2 in the afternoon, where water usage is much higher. Seasonal, there might be some seasonal variation in water being provided to the municipality, and that will really depend on the municipality as to when they may have high or low seasons for water supply. And then recording elevations, of course, the elevation of the water supply in relation to the sprinkler system is critical. I'm not going into any detail on that. It's like I say, it's not complicated, but it takes time, and there's so many other good resources out there that I don't think I really need to go into that. But I do want to comment on a few things. Here's a pressure gauge. That's a perfectly good gauge. They're actually nice gauges. These are 10 years old. If you notice something about them, no real identification other than the manufacturer's name. I have no idea as to when these were last calibrated. They haven't been calibrated. In fact, these gauges for testing purposes should be calibrated on an annual basis. There should be a tag affixed indicating the calibration house that conducted the testing. So I have no real idea as to whether or not these gauges are accurate. Here's a pitot tube. On the left side, there's a nub with a little hole in it. You cut that end into the stream. It records the pressure. You'd see in the middle there. There's a stub where a pressure gauge would be installed, and you record the gauge, the pressure, and as I said, converted into a flow. Not all pitot tubes are created equal. This one is, I use this one because it's easy to use for lower pressures, but it's hard to cut in and get the right pressure for really high flows. You need to be able to keep the unit stable in the flow. There really is a certain art to getting the right number. It's got to be in the middle of the flow, and I think 1/2 the distance from the opening, the size of the opening. So it's the reason there's so much variation in pitot pressures. When I look at someone doing a test, I'm looking at how they care for their gauges, whether or not they're calibrated, and I also look at the pitots that they're using, and I get a pretty good sense of just how accurate these numbers are going to be. One other point before we move on to our estimating of water supplies. We'll be developing a water supply curve, and we'll be using this graph paper right here, and it's a semi-log paper. So on the y-axis, it's linear in pressure, and on the x-axis, it is to the N18.5 power in GPM and flow. And what you would do is on the left-hand side for no flow, that static, you would record your pressure. And on the right side, let's just say it's 500 at 50 psi, 500 GPM at 50 psi, you'd record that number with the next, and you draw a line between the two. We'll go into that in a little bit more detail. We are going to focus on conducting a 2-inch drain test for our estimated water supply. To start that off, we need to obtain some pressures, a no flow pressure and a flow pressure. And on the riser will be a tag, or there may be some paperwork in maybe a plastic holder. There'll be 2 sets of numbers. There'll be a higher number and a lower number. 95, 85, 75, 45, whatever, but there'll be 2 sets of numbers. The higher set's the no flow, and the lower pressures is the flow situation. And we're going to use those 2 numbers as the basis for our water supply test. There may be 10 different tests on this tag, so I throw out the high, I throw out the low, and I'd use the number that was most represented on the tag. The other piece of information we'll need to estimate water supplies is the setup of the 2-inch drain. So the 2-inch drain, and this is for our purposes, we're only looking at 2-inch drain work here, because that's the graphs that we're using are based on 2-inch drain tests, piping. So there'll be an angle valve, as you see there to the left, and then there'll be a 2-inch line extending out. And it'll generally, like this one's right against the block wall, it will it'll elbow out and run outside the building, typically to a 45 to the ground. We're going to need that setup. I would ask you to do a search for the AXA XL guideline of water measurement using 2-inch drain test. It's PRC 14122. And what it will do is it's a short document, but it will provide you guidance on being able to convert those that 2-inch drain configuration and water pressures into a flow. In that document, you'll see in Table 1 in equivalent length for fittings. So for instance, that angle valve that we saw in the prior slide has an equivalent length of 29 feet. The elbows and the 45s have a respective equivalent length of 5 and 2 feet. So we're going to use that information to for the graph that's coming up. And here is that graph. So on the left side is the pressure. On the x-axis is the flow. And those series of curves are the equivalent length that we've determined from the 2-inch drain setup. And we'll do an example so that we can understand exactly how we use this chart. Let's just go through the procedure. We're going to determine the equivalent length of the 2-inch drain. We're going to ensure that it is a 2-inch drain. And we're going to ensure that the testing has been done with valves wide open. You're not likely to get to handle any of this stuff now, so you're going to have to take this in good faith. This has all been conducted. When I started in the business, we literally touched everything. We reset dry valves. We flowed hydrants. I did my own fire pump test for 20 years with my own equipment. Including doing the multimeter testing inside the controllers. So we did a lot of things that just aren't doable now, but know that there is a procedure to obtaining the correct information. Let's just look at an example here. So we went to the tag, and the tag had a bigger number and a smaller number. The static, the no flow was 75 PSI. And the residual, the lower number, the flow number, was 65 PSI. We sketched out the piping from the riser to the outside. It had 6 feet of 2-inch pipe. It had one angle valve, had one elbow, and it had one 45 degree. And from that, we determined from Table 1 that the total equivalent length is 42 feet. So if you recall from the prior slide, we had a flow pressure a residual of 65 PSI, and we had 42 feet of equivalent length of pipe. So going from the y-axis over at 65 PSI, stopping shortly before the 40 equivalent length of pipe, and then drawing a vertical line down, we end up with somewhere around 410, somewhere in that area, GPM. And if you were to look at that water supply curve on the semi-log paper, it would look something like this. We had a no flow situation of 75 PSI. We had a flow situation of 65 PSI, and we determined from the prior graph that the GPM was 410 GPM, which we recorded as the second point. We connect those two points, and that becomes the basis for our water supply curve. Is that in fact what would happen with the water supply curve? Truth is, you really don't know what the water supply is beyond that 410 GPM flow, but we take it as an act of faith that the water supply will continue along that path. I say that with some confidence because I've done testing where the numbers have dropped off like a rock because there's been obstructions or other issues. So um, it's uh, it's something that we take as good engineering judgment that the supply curve is in fact accurate, but always know that it's best to flow out past the overall water demand of the sprinkler system to ensure that you have adequate water. And then I just threw in a number here from one of the prior matrices that we had used to calculate a sprinkler system. We had 578 GPM required at 49 PSI at the base of the riser. So you can see that point sits below the curve, which indicates that we have adequate water for the sprinkler system. Now I'm going to get into, once I start doing the hydraulic systems, I'm going to get into some pretty interesting stuff with supply system curves and start to play around with them and show you how to extrapolate numbers from them. It's going to get pretty interesting. But right now, what we're able to do is we're able to now sketch out a water supply curve. We're able to pinpoint our estimated demand based on those 5 prior presentations that I've done and come up with some basis for determining the adequacy of a sprinkler system. You'll see calculations that will be to the second decimal point. I mean, in this case, for instance, let's just say as in our prior example, the sprinkler demand was 578 GPM at 49.52 PSI. You should, after having seen all of my videos, calculate the second decimal point. It's a pretty amusing thing to do for any number of reasons. There's a lot of hocus pocus and best guessing going on, even when things are done absolutely correct, not to mention the estimating that we're playing around with. That's not to denigrate what we do. I think I've been a fire protection engineer for many years. I respect what we do, and I respect the history and the development of what's been done. Without fire protection engineers and fire protection community in general, America in the 19th century would have continued into the 20th century burning to the ground, which it did in many cities. So we should all give ourselves a pat on the back as fire protection engineers. Having said that, if you've watched my first video, this is not F equals ma. This is not Newton's laws. There's a lot of best guessing and using what is closest to the most accurate to come up with the number. And so we should never be doctrinaire in what we're doing and always appreciate the limitations in these calculations. That kind of concludes the first part of this pipe schedule and now estimating water supplies. We're going to now start to look at calculating hydraulic systems, backing into some numbers on that, extrapolating based on the system curves. You're going to be able to do some pretty interesting things when this is all over. So stay tuned for more.